Welcome back, Physics 30. This video will discuss what you do with the Photoelectric Effect lab/tutorial. So you have this booklet, and what you'll have to do is to go on to Google, because it uses a little simulation. You can find it by typing in PHET simulations, and we'll go into the physics section when you get to there. And what we want to grab, go into quantum phenomena and then the photoelectric effect, and then we'll download it. And yeah, it gives us a little information, but it could harm your computer. Do you want to continue anyway? Yes, because we believe it's safe. So we'll just wait for that to open. And there we go, starting up. Yeah, so it looks something like this. Alright. So going through this, and what happens here is that we can increase, if we have a light bulb here, we assume this is all in a vacuum here, and we have electrons being emitted. We can increase the wavelength or decrease the wavelength. And of course, wavelength and frequency are inversely related. So if we decrease the wavelength, we're increasing the frequency of the light, and that's what gives the photons more energy. Now, if we look over here, I'll go into options, because one thing you'll have to do is show photons. So we'll show the little particles of light coming out, and if the interesting thing is here, now we could pick different things here too, whatever this metal is, whether it's sodium, zinc, copper, or whatever. Let's stick at sodium for now. So we can see at, I'll just increase the intensity or the brightness of the light there. So we can see we're sending photons out, but that's what those represent. And they're moving at a certain speed, of course. If I decrease wavelength by increasing frequency, you can see they change color, yellow, green, etc. And as I increase the frequency, if I compare down here, the number of photons being sent, and if I decrease the wavelength, which is increasing frequency, to here, you can see I have less. Okay? And of course, one of the things you'll see is that this light dislodges electrons from the piece of metal here, causes them to go flying from one side to another. And when I'm going here, they're relatively slow, as you'll find out in this little tutorial. Or if I find the cutoff point here, see, so they're going relatively slow. I have quite a few photons. If I increase the frequency, I have fewer of these photons, and you can see I have the electrons are going extremely fast. So one thing that you need to realize is that at low frequencies or high wavelengths, we send out a lot of photons. As we're increasing frequency, we must be increasing the energy of these photons, because they're giving the electrons more energy. And also, the light bulb can only supply so much energy. So if we're sending out photons of larger energy, where that energy is absorbed by individual photons, so there are fewer photons at the higher energy levels or high frequency levels. Okay? So this is what we'll be adjusting, the intensity meter. Also, the voltage of the battery here can be adjusted. You could also change it to opposite poles as well, and that's what we'll be looking at in the actual lab. A couple of things to note here that I want you to add. For number 3 here, it talks about reset the intensity to 0, test yellow light and green light shining on the metal, at what exact wavelengths are electrons first dislodged from the surface of the sodium. So in order to do that, you set the intensity down to 0. When you go to yellow and green, increase the intensity again, so you can have the light actually turned on. And down here it says reset the intensity to 0 and move the color slider to a shorter wavelength. To expect to see electrons ejected from the surface of the metal. Test your prediction, and then again, once again, increase the intensity so you can actually see it. Alright? Now, before you go into this, we have to know a few things. So if you could grab a piece of loose leaf, a couple of notes you need to copy down. Let's see, I think I have them before here. Here they are. So a couple of things that you took back in Physical Science 20, of course, the universal wave equation. So treating light as a wave, we could do that. If we treat light as a wave, since light moves at the speed of light, we have C is equal to lambda F, where frequency is in hertz or seconds to the -1. Wavelength is in meters. And the interesting thing about this is that we're using the equation as if light is a wave, but going with the photoelectric effect, we're treating light as little particles, little packages, little photons. So we're treating it like particles. You can think of them almost like little marbles come flying out of there and hitting the electrons and possibly dislodging them from a specific metal. So that's the interesting thing about wave-particle duality. We think of light as waves, we also think of it as particles, depending upon the circumstance. So looking at the energy of the photons or photon, we talked a little bit about in our last video, E equals hf, where h is called Planck's constant to make the equation work, and f is still in frequency. So Planck's constant is 6.626 times 10 to the minus 34 joules per second. So of course this seconds, we have that, and everything will cancel out so that we end up with joules as our energy value. And of course what we could do here, the relationship between frequency and wavelength, if I solve this for frequency, divided by lambda, so f could be represented as c over lambda. So instead of having this, I could have c over lambda for f. So you may have to use that idea. And with our situation, we're dealing with voltages. When dealing with wavelength in nanometers, such as what we will be doing in that lab, 1 meter, of course, is 1 times 10 to the 9 nanometers. And if we're dealing with electron volts for our energy, so we'll be looking at certain voltages here. So we're not going to be dealing with joules. There's a good way to rearrange that equation when using those units, and you'll be using this through most of the lab as well. Energy, in this case, will be in electron volts, or just EV. And we have wavelength on the bottom again, but instead of being in meters, it's in nanometers. And to make it work numerically, this top value will be 1.240 times 10 to the 3 electron volts times nanometers. So of course nanometers and nanometers will cancel, and we're left with electron volts. So this top number here represents a combination of Planck's constant and the speed of light with units rearranged such that we get our energy value in electron volts when we're using wavelengths in nanometers. And that'll be very handy because you won't have to do that conversion constantly in the tutorial there. Alright. Also, when the energy of the light photons is used to emit electrons from metal surface, so there's two things that happen here. Part of the energy that a photon has is used to simply dislodge the electron, and any leftover energy is used to make the electrons go from the left to the right here. So two things are happening here. We have the energy supplied by the photons is first used to dislodge the electron. In the textbook it's W naught. In the lab it's the Greek symbol phi here, but both of them refer to the work function or amount of energy required to dislodge an electron from a metal. And then Ke max, kinetic energy max, is that once the electron has been dislodged, what energy is it traveling with then? Okay, so the energy supplied by a photon does two things: dislodge it and give it moving energy, kinetic energy. Okay. What you'll also be doing in that lab is solving for, okay, what is the maximum kinetic energy? We have our total energy. We've used up part of it to dislodge it. What energy is left to make it go? To make it go from one side to the other, moving energy. And of course, the E here is simply E is equal to HF or HC over lambda. Okay, so we can represent it that way. So we'll be using this equation throughout, and the big one here is this one here, using units of nanometers for wavelength, and this unit here referred to as electron volts, and then looking at energy in terms of electron volts. Alright, we'll see you again. If you have any issues, just call me over and I'll give you a hand.